Hey folks, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to quantify the equilibrium concentrations for both products and reactants, as well as the equilibrium constant Kc or Kp. Now, this can be accomplished by utilizing the mass action expression in conjunction with something that's known as an ice table. So let's go ahead and get started. Now, the trick to quantifying the equilibrium concentration for both products and reactants is to be able to describe mathematically the progress of the chemical reaction from start to finish. To better understand this point, I want to draw your attention to this graph that describes the conversion of reactant A into product B until a state of dynamic equilibrium is achieved for this chemical system. And so once again, if I wanted to determine the equilibrium concentration for these two substances, the reactants and the products, I need to somehow describe the progress of the chemical reaction from start to finish mathematically. And so it turns out that we can do so by cutting up, if you will, this progress of the chemical reaction into three phases or three steps. And so the first phase that we want to mathematically describe is the initial concentration of the reactants and the products. And so we can think about the initial concentration as our reference point, or the start, the concentration of the reactants and products that we're starting with. And so the next thing that we want to describe is how those concentrations changes in the course of the chemical reaction until the equilibrium concentration is reached. And so this whole entire section of the graph or of the progress of a chemical reaction can be described as simply as the change, or change in the initial concentrations of the reactants and products. And finally, once the chemical system has reached a state of equilibrium or dynamic equilibrium, we can go ahead and define that point as the equilibrium concentration for both of those substances. And so we can think of the equilibrium concentration as the final outcome, or the final concentration that the reactants and products will have once the chemical system has reached a state of dynamic equilibrium. And so it's really easy for us to mathematically describe the initial and the final concentration. However, what's a little bit more challenging is being able to mathematically describe the change in a chemical reaction, because each chemical reaction progresses differently. We can't really put a hard number to this change. But the beautiful thing about this is that we can represent the change of the concentration of the reactants and products as a variable. And so let's just say that we have an initial concentration of 1. And so as the chemical reaction progresses, the concentration of the reactants is going to decrease until such time the chemical system has reached a state of chemical equilibrium. And so because there's a decrease in the concentration of the reactants, we're just going to simply put a minus sign. Oops, I kind of jumped ahead of myself, but that's okay. So we're going to go ahead and put a minus sign. And so generally, since we don't know how much change is going to occur, we're going to represent the change as simply a minus x. Okay, so this variable is going to represent the unknown change that's going to occur in the system. And in a very similar logic, we can go ahead and apply that to products. So since products is going to increase as a reaction goes in the forward direction, then we're going to describe the overall change in the concentration of products as a positive value because we're producing substances, we're not consuming it. And we're also going to represent the change in the production of products as a variable, which in this case is x. And so this x, once again, allows us to mathematically describe the overall change that's occurring between the two concentrations of the reactants and products. And so instead of describing the progress of a chemical reaction graphically, we can still represent this entire reaction progress by creating a table. And since we're using the initial change in equilibrium as the three phases or the three steps in that table to describe the progress of the chemical reaction, we've come to this acronym that's known as an ICE table, where the I in ICE is going to represent the initial concentration. The C in ICE is going to represent the change. And the E in ICE is going to represent the equilibrium concentration. And so whenever you guys create an ICE table, I really encourage you to rewrite the chemical equation. And then when you guys are building the ICE table, you're going to create as many columns as it needs. But in one of those columns, you're just going to put in I, C, and E, which is going to represent the initial concentration, the change, and the equilibrium concentration. And so the initial concentration, actually, let's go ahead and take a look at these columns. And so this column here is going to represent the initial concentration for substance A. This this part in the column is going to represent the change in the concentration of substance A or reactant A. The same idea goes here for E, right? So this is going to be the equilibrium concentration for substance A. And so we can go ahead and apply that same logic for each of these three spaces, where this space is going to represent the initial concentration of product B. This space is going to represent the change in concentration for product B. And finally, this space is going to represent the equilibrium concentration for product B. All right, so now that we have a better understanding of what this table is going to represent, let's just go ahead and put in some notations here. So once again, this space is going to represent the initial concentration for reactant A. And C is going to represent the change. And so we're always going to assume that the forward reaction is going to occur. There are some differences in this scenario, but it really depends on the numbers that's provided for you. And we'll take a look at an example in just later on. And so C is going to represent the change for reactant A. And we know that since it's going to be consumed, the reactant is going to get a negative sign, and then we're going to put an X here. And this X is going to represent the unknown concentration. And so for the product, here we can go ahead and put in the initial concentration of the product, product B. And since product is being produced, we're just going to go ahead and put a positive sign. And then we're going to put X as a variable because we don't know how much it's changing, but we do know that there's going to be some change in concentration. And so what's really important here is for you guys to make sure that the stoichiometry between reactants and products is represented in the change. And so it's not enough to just say minus X plus X. We need to involve the stoichiometry between these two substances. So here in this case, it's going to be minus 2X and then plus 3X. And so it turns out that to mathematically describe the equilibrium concentration, it's simply the sum of the initial and the change. So let me go ahead and put this here, maybe a different color. Let's do green. And so it turns out that the initial concentration plus the change is going to equal the equilibrium concentration. And so the last column, we're just going to go ahead and carry down the sum of these two. And so here we have the initial concentration of substance A plus negative 2X. And then this is going to be the initial concentration of B plus, if you want, you can write another plus 3X. Okay. And so if I were to simplify my signs, I would simply get the equilibrium concentration of substance A as the initial concentration of substance A minus 2X. And then this can be simplified to the initial concentration of B plus 3X. Okay. And so this is typically how we fill in the ICE table. And once again, the ICE table is representing three key phases in the course of the chemical reaction as it progresses from start to finish. Okay. All right. And so now that we've kind of understood the logic behind the ICE table and what it's trying to describe, we're going to go ahead and apply the mass action expression and the ICE table to quantify the equilibrium concentrations for both products and reactants, as well as the equilibrium constants, Kc or Kp. All right, so let's go ahead and look at our first problem. Here we have hydrogen gas and iodine gas, and at some point in time, it's going to come to some type of chemical equilibrium with the product hydrogen iodide. And this reaction is happening at 425 degrees Celsius with an equilibrium constant of 55.64. And so real quick, as a way of review, before we continue on with the problem, remember that the value of Kc informs us of how the relative concentration of the products and reactants will be at equilibrium. And so if you recall from a previous lecture, if Kc is far, far greater than 1, then we know that the concentration of the products is going to be favored at equilibrium. In other words, it's going to be much larger than the concentration of the reactants at equilibrium. So let me move this over to the right just real quick. Okay. And so we're going to go ahead and kind of prove this concept mathematically. So let's go ahead and continue. And so if you have 1 mole of hydrogen gas and iodine gas, and it's placed in a 0.5 liter flask at this same temperature, the question is asking us what the equilibrium concentrations of these substances are. Okay, and so I'm just going to go ahead and highlight the main question. So what is the equilibrium concentration of these substances? And so how would we go about and figure that out? How do we quantify the equilibrium concentration of H2, I2, and HI? Well, let's go ahead and go back to the beginning of this lecture video. And I want you guys to see that the equilibrium constant and the mass action expression describes everything that's at equilibrium. And so if I wanted to determine the equilibrium concentrations of H2, I2, and HI, the first thing that I want to do is build a mass action expression or an equilibrium law. And to build a mass action expression or equilibrium law, I need to utilize my balanced chemical equation. And so I need to make sure that my chemical equation is balanced. So here I have 2 hydrogens, 2 hydrogens, 2 iodines, 2 iodines. Okay? And so once it's balanced, I'm just going to go ahead and write a mass action expression. And so since Kc is given, I'm going to go ahead and write everything in terms of concentration. So Kc is equal to the equilibrium concentration of hydrogen iodide. And so since there's a coefficient of 2, I need to raise this to the power of 2. And then I'm going to divide this by the concentration of H2 gas at equilibrium raised to the first power times this by the concentration of I2 gas raised to the first power as well. Okay. So whenever you guys are using the equilibrium constant, that means all of these concentrations must be at equilibrium. And so now that I've defined the equilibrium concentrations by using this mass action expression, I can go ahead and plug in 55.64 into Kc. But it really doesn't help me any if I don't know any of this. And so to determine the equilibrium concentration, I need to go ahead and build an ice table, because once I have a mathematical expression for the concentrations of each of the substances at equilibrium, then I can go ahead and plug it into this mass action expression and continue to solve the problem. Okay? And so I need you guys to make those links. So here we have equilibrium concentration, and this is also describing the equilibrium concentration. So that means that I need to build an ice table. Okay. And so I'm just going to go ahead and rewrite my balanced chemical equation. Okay. So make sure that you guys are including the substance and the coefficient. And when you guys are building the mass action expression or the ice table, make sure that you guys are ignoring all the solids and liquids. Okay. So notice that I'm building essentially 4 columns, right? The first column is for I, C, and E, but each column is going to represent the substance that's in my balanced chemical equation. And so if you recall I, it's representing the initial concentration. And so since, let me see if I can, I'll just do it over here. Since I is representing the initial concentration, it needs to be in unit of molarity. And we know the molarity is moles per liter. And so if you read through the problem, notice that we have 1 mole of H2 and 1 mole of I2. And it's placed in a half a liter of flask. And so I can determine my initial concentration of hydrogen gas as simply 1 mole for every 0.5 liter. And so if you plug this into your calculator, you guys are going to get 2.00 molar. I think this was 3 sig figs here. And so this is an exact number. So overall, we'll just keep 3 sig figs. And so since I have an equal concentration of iodine, then I also know that my initial concentration of I2 is equal to 2.00 molar. Okay. So here I have 2.00 molar concentration of H2, 2.00 molar concentration of I2. Now let's go ahead and talk about the initial concentration of HI. In the problem, is there any clue that would determine what the initial concentration of hydrogen iodine is? The answer is no. And so if there is no indication what the initial concentration of HI is, then you're just going to say it's 0. So that makes sense because right now you have pure reactant in your reaction vessel. And so the reaction has not yet started. You just mixed these two substances in your flask. And so as the reaction progresses, then you'll build up your product. But initially, you typically don't have product if you're just starting a chemical reaction. Now, let's go ahead and talk about the change. So if you guys recall, the change requires three parts. One, the sign. So minus means consumption, plus means production. The coefficient, and the variable, which is just going to be x. And so here in this case, since there's 1, 1, and 2, then this is going to be minus 1x, and plus 2x. And so to calculate the equilibrium concentration from this ice table, remember that we're simply adding I and C. So we're going to add these terms down. Okay. And so if we add this down, what we get is 2.00 minus 1x. Okay. 2.00 minus 1x. And 0 plus 2x is simply 2x. Awesome. And so the really cool thing about this is that we've now created mathematical expressions for the equilibrium concentration for each and every single one of these substances. So even though we're not, even though we haven't solved the problem just yet, it's getting us closer to it. And so once we have the equilibrium concentrations, then we're going to go ahead and plug in every single one of these terms into the mass action expression. And so I'm just going to go ahead and kind of copy and paste this right here. Okay. And so I'm going to go ahead and take this term and plug it into H2, take this term, plug it into I2, and take this term and plug it into HI. Okay. And so the resulting, the result that we get is, and I'm going to plug in the value for Kc, which is 55.64. So what we get is 55.64 is equal to 2x. Now, remember that there's a squared, so please don't forget your exponent. So 2x squared over 2.00 minus x, that's for the H2. And it's the same thing here for I2. And so I'm just going to go ahead and put in times 2.00 minus x. Okay. And so if you guys are looking at the resulting equation that we get, it looks like the denominator can be combined because they're the same term. And so the result of the combination of those two terms is simply going to be 55.64, which is going to be equal to 2.00 minus x squared. So it's being represented twice because they're being multiplied. And so what we get is 2.00 minus x. And everything is squared. Let me move this down. All right, so our goal is to currently solve for x, just because that's what algebra tells us. And so we want to essentially get rid of these exponents. And it's pretty cool because they're the same. So what we can do is take the square root of the whole entire term. And so this square root is going to cancel out both of these, both of those exponents. And so what we do to one side, we have to do to the other. So we also have to take the square root of 55.64. And so what we get is simply 2x over 2.00 minus x. And let me see here. Let me plug in the square root of 55.64 real quick. So square root of 55.64 is equal to 7.459. Okay, let's just go ahead and keep the same number of sig figs there. All right, and so from here on out, this just becomes algebra. So what we're going to do is multiply 7.459, I'm sorry, we're going to multiply 2.0 minus x to the other side. So I get 7.459 parentheses 2.00 minus x equals to 2x. And so I'm going to go ahead and distribute that 7.459 into each of those terms. And so what I get is 14.92. And then I'm going to go ahead and distribute that over here. And what I get is minus 7.459 x equals to 2x. And so I'm going to combine like terms. So I'm going to add this value to both sides. And so that's going to leave me with 14.92 equals to 9.459 x. And so I'm going to go ahead and divide this to the other side. And so therefore x is going to give me, so 14.92 divided by 9.459. So that's going to give me 1.577. Okay. And so it's great. You know, we solved for x, which is really awesome, but we actually did not solve, we did not address the question. So when you solve for x, when you guys do these, when you apply the ICE table into the mass action expression, it's only describing the magnitude of that change. And so what we're doing is we're trying to solve for the equilibrium concentrations of all three of these substances. And so now that we solved for x, what we're going to do is we're going to plug x back in to this portion of the ICE table, because this is going to represent H2, the equilibrium concentration of H2. This is going to represent the equilibrium concentration of I2. This is going to represent the equilibrium concentration of HI. Okay, so I'm going to go ahead and just copy this real quick and bring it over to this side. Okay. Let me erase some stuff here. All right, and so it is these terms that I want to plug back in. And so the equilibrium concentration of HI is defined as 2x, or 2 times 1.577. And so if I plug that into my calculator, I'm going to get 3.154. Okay. Now, since we're talking about concentration, then the final unit must be in molarity. Okay. And so if you look at both the equilibrium concentration for H2 and I2, it's defined by the same expression. So I'm just going to go ahead and represent both of them in one go. So the equilibrium concentration of H2 and the equilibrium concentration of I2 is defined as 2 minus 1x, or 2 minus x. 2.00 minus x. So that's going to be 2.00 minus 1.577. And so the answer that I'll get is going to be approximately 0.42. Okay. So notice that the last operation, if you recall, it's you have to apply the rules of sig figs for subtraction, which means you have to record the least number of places after the decimal. And so here we have 2 decimal places, 3 decimal places. And so therefore, we can only record up to 2 places after the decimal. So we need to round down. So this is going to be 0.42 molar. Okay. And so the equilibrium concentration of I2, or I'm sorry, not I2, HI, let me rewrite this. So the equilibrium concentration of HI is 3.154. The equilibrium concentration for H2 and I2 is going to be 0.42 molar. Now, if you guys recall, at the very beginning of this lecture video, I made a statement saying that since the Kc is far, far greater than 1, the concentration of the products must be greater than the concentration of the reactants. Well, did we prove this concept true? Does our math reflect that concept? And it does. So this is a product. So 3.154 is greater than the concentration of the reactants. Okay? So this is describing the scenario in which Kc is far, far greater than 1, and therefore the concentration of the products at equilibrium is going to be greater than the concentration of the reactants at equilibrium. And so if you wanted to take this one step further, the graph that best describes a Kc value that's far, far greater than 1, so in which this is going to represent concentration against time, that this is going to be the scenario in which the concentration of the products is going to be much higher than the concentration of the reactants. So this is going to be H2 and I2. And so if we kind of extrapolate those 2 points, then we get a graph that looks like this. Okay, so this is our concentration versus time graph that describes the progress of the chemical reaction until the chemical system has reached a state of dynamic equilibrium. Okay. All right, so hopefully you guys are seeing how these concepts that we've kind of gone over, these past few lecture videos are being tied in through this topic. All right, so not every single problem is going to be like what we worked on. There's going to be variations into how we tackle equilibrium problems. So let's go ahead and go over another problem just to gain some more experience. So reading through example number 2, we have this chemical reaction. And so reading through, if 1 mole of NaCl, which is a product, was placed in a 2-liter reaction vessel, and the equilibrium concentration of NaCl was found to be this amount at 500 Kelvin, determine the value of Kc. So here in this case, we're not actually concerned about solving for the equilibrium concentration. What we want to solve for is the value of the equilibrium constant Kc. So let's go ahead and rewrite this chemical equation, and we're going to use the chemical equation to help us organize our given values. So here we have 2 NaCl, or I'm sorry, 2 NO plus Cl2 to produce 2 NaCl. Okay. And so reading through the problem, it says that we have a 1 mole sample of NaCl that was placed in 2 liters. And so maybe I'll put this in gray. We have 1 mole in 2.00 liters. And this problem also told us that the equilibrium concentration of the same substance is this value. So I'm just going to go ahead and put it off to the side, that the equilibrium concentration of NaCl is going to be 0.220 molar. So from this given information, we want to determine the equilibrium constant Kc. All right, and so if I want to determine the equilibrium constant Kc, that's going to come from the mass action expression. So the only thing that we know how to solve for Kc for is by building a mass action expression. And so looking at the chemical equation is just simply the mass action expression is the concentration of the products over the concentration of reactants raised to its own power. And so this is going to be the concentration of NaCl at equilibrium raised to the second power, because we have a coefficient of 2. Divide this by concentration of NO raised to the second power, times this by the concentration of Cl2 raised to the first power. Okay, so here we have 2, 1, and 2. And so we want to be able to solve for this. And the only thing that we know is that the equilibrium concentration for NaCl is 0.220. And so if we're able to figure out the equilibrium concentration for the other 2 substances, then we can go ahead and put all of these numbers together to basically solve for Kc. And so since we need to determine the equilibrium concentration for both of these substances, that's going to prompt us to build an ice table. And so here I'm going to put in ICE. So initial, change, and equilibrium. And so I'm going to go ahead and create a table that'll help me organize the initial concentrations, the change in concentrations, and the equilibrium concentrations for each of these chemical species. And so, looking through the problem, do we have initial concentrations for nitrogen monoxide and chlorine gas? And the answer is no. And so we're going to go ahead and just put in 0 here and 0 here. Now, it turns out the only piece of information that this problem provided is the initial amounts of the product instead of the reactant. And so we're going to go ahead and divide these two values. So 1 divided by 2, that's basically 1/2 or 0.500 molar concentration. Okay. So I'm just going to go ahead and put a bracket here. Okay. All right. So now that we have the initial concentrations listed out, let's go ahead and talk about the change. So if we have an initial concentration for product and no initial concentrations for the reactant, how do you think the chemical reaction will shift? Okay. And so the chemical system will go from the products to the reactants. So this time we're working in reverse. So in this scenario, we're going to consume products, so it's going to be minus, and then since we have a coefficient of 2, it's going to be minus 2x. And we're going to produce reactants that reflects their coefficient, so 2 plus 2x and plus 1x. And so the equilibrium expressions that we get is simply the sum of I and C. So we're just going to add down. So this is going to be 0.500 minus 2x. This is going to be 1x, and then this is going to be 2x. Cool. And so it's important for us to not get into the habit of taking these expressions at equilibrium and then plugging it into the mass action expression. I mean, we'll do that plenty of times, as you guys will see in as this semester progresses. But we have to kind of keep in mind here that the equilibrium concentration of NaCl was already provided for us. And so we can actually use this to solve for the value of x. So how do we do that? Remember that this is the expression for the concentration of NaCl at equilibrium. And so we can say that 0.500 minus 2x is equal to 0.220 molar. Okay, so I'm going to go ahead and put an arrow down here as well. And so if we simply focus on this expression, we can solve for x. And once we solve for x, we can go ahead and plug in that value for wherever we see x in the row that describes the equilibrium concentration for those substances. And so here I'm going to rewrite this. So 0.500 minus 2x is equal to 0.220. So I'm going to first subtract this out. So this is going to be minus 0.500 minus 0.55 or 500. Okay. So here I have negative 2x is equal to, so give me a second, let me plug that in. So 0.220 minus 0.5, that's going to be minus 0.280. Now I'm going to divide by negative 2, divide by negative 2, and so my value of x is going to be negative 0.140. And so this x is what I'm going to, oh, I'm sorry, not negative, it's positive, because negative divided by negative is positive. So let me get that out. Okay. And so I'm going to go ahead and plug in this value wherever I see x. Okay. And so then this tells me that the equilibrium concentration for Cl2 is 0.140 molar. And this also tells me that the equilibrium concentration for nitrogen monoxide is going to be defined as 2x. That's going to be 0.280 molar. And we already know the equilibrium concentration for NaCl because this was given to us in the problem, which was 0.220 molar. So that's awesome. Now that we have the equilibrium concentrations for all of these substances, we can now go ahead and plug in all of these numbers in the mass action expression to essentially solve for the equilibrium constant Kc. And so I'm going to go ahead and just copy this real quick. I'm going to go ahead and put this at the bottom here. And so I'm going to draw some arrows. Okay, so the Cl2 goes there, the 0.28 goes here, and the NaCl goes here. Okay. And so Kc is going to equal to parentheses 0.220 squared over NO is going to be 0.280 squared times this by 0.14 to the first. Cool. So now that we have all of our numbers in the mass action expression, we can go ahead and solve for Kc by plugging everything in the calculator. So I have 0.220 squared, divide this by 0.280 squared times this by 0.140. Okay. All right, so the answer that I get is going to be 4.41. So my equilibrium constant is going to be 4.41. And that's pretty much it for this problem. Now, I know that you guys are probably thinking that Kc is greater than 1. And so, therefore, the equilibrium concentration for the products must be greater than the equilibrium concentration of the reactants. And so if you guys are looking at the equilibrium concentrations of both products and reactants, I do want you guys to notice that there is more concentration of reactants than there is products. And that's because the Kc value it's not very large in magnitude. So this actually is closer to 1 than it is far, far greater than 1. And so here, when that scenario occurs, we kind of have a strong presence of both reactants and products at equilibrium.